Okay, let's talk about Schrödinger equation. Today we will be having a proper uh, derivation of Schrödinger equation. Now, uh, so we know that the formal or the proper equation for Schrödinger equation is for the normal general form, which is H, which is Hamiltonian operator, equals p square over, or not p square, let's get from the basics, k dot e plus pe, and this, or let's remove p for now, we will add it later on, I'll tell you the reason for it. Okay, so now we know that k dot e is nothing but kinetic energy, which can be written as 1 by 2 mv square. Okay, now this can further be um, it can further be like we can make our required equation with which we will be able to make the Schrödinger equation, and that is, we do 1 by 2 m over m, we divide m with, we multiply with m and then divide with m, and of mv square. That's why we get over here this 2m combines, because we get 2m, and m times m is m square and v square. So we know that in classical physics, p is equal to mv is nothing but momentum. This is momentum, which is nothing but rate of change of force. Well, if we write it mv is equals to ft, then the rate of change of force is momentum as well. So momentum is is a product of mass and velocity. So this becomes, so if p equal mv is momentum, that means m square and v square is equals to p square, means double the momentum or square the momentum, which is p square over 2m. Now this is our form in which h, let me write h now. Now this is our way in a form, our form in which about the particle which is traveling, the kinetic energy of the particle which is traveling. That's what we got as a general form. Now here, please be noted that p is actually a operator. Okay, it's called linear momentum operator. Okay, denoted as p. Now, and m, we all know that m is nothing but the mass of the particle. So this is the expansion of k dot e into the general form of the Schrödinger equation, which of course is official. We can go further into it. We will get the full Schrödinger equation by using the Hamiltonian mechanics. So then what we do is that we uh, let me write what p is actually in terms of momentum. Oh, sorry, in terms of quantum mechanics. P is product of this I, h lambda, and this. We will talk about what each of these are. Now, we will talk about what each of these are. Like I think all of us are very familiar with I, which is the complex number, and H is sorry, let me get the h straight. H is not h, actually it's h bar. H bar is the reduced Planck's constant, which is nothing but the normal normal h Planck's constant divided by 2 pi. So which gives us, if you want to calculate the value of h bar as of for general knowledge, the value of h is 6.2626 times 10 to the power minus 34 over 2 pi. You'll get the value of h bar, and I think if I'm right, h bar's value is 1.05 times 10 to the power minus 34 joules second. That's the unit for both. For the unit doesn't change as we are multiplying the value of h with a number n or 2 pi. There's no unit with it has no unit, so the unit doesn't change. Now the main thing over here is this guy, because these are constants, but this guy over here is a, and actually I has a special mean value, which is square root of n minus 1. And the reason for this is that we all know in mathematics we cannot take square root of -1. We'll get error, math error. Now coming back to this weird symbol, which is I think we are familiar with this symbol. We all are familiar with this symbol, and in physics, this symbol means change of momentum. Sorry, change in. The literal meaning is change in. So how I recognize it is I take the I take it like opposite. I turn it around, and the main thing which keeps is about important is the thickness of this thing. Like if you want, you can just know about it, but it's not necessary. But what it's actually, this is also an operator. Okay, it's an operator. Just like the linear momentum operator, and if we have further more operators, I'll tell you about them as well. This is called gradient operator. Gradient operator. Okay. Now, what this gradient operator is I think by gradient operator you might have noticed, yes, it's nothing but derivation, d over dx. Derivation with respect to dimension. It's a dimensional. It's a dimension. We're talking about a dimension and how many dimensions we're looking at the equation. So uh, now what we do here is we are going to expand. Now we have p square, which is the main, and one more thing, this h is also a operator, which is Hamiltonian operator. Okay, which is known as for the formula. The formula is sorry, not the formula. What this operator actually is, the full form of this operator is uh, I h bar d over dt. Now, what's common between momentum and the Hamiltonian formula? What is common? Yes, the common is these constants h, I, and h bar. These are common. The only difference now we have is that in momentum we were looking at the the position, and for the Hamiltonian we are looking at time, with respect to time, but momentum we are looking at in this with respect to um, uh, uh, position. So expanding the equation, now that we know about the operators, h bar, now we can write the equation as expanding. Let's expand the equation. Expand the equation. Now what do we get when we expand the equation? We have the formula, so we can easily do it. The formula is h bar is nothing but p. So now we are replacing p. We'll write h is minus h bar square over 2m. Because of the square we are getting it. Okay, now square, and yeah, this is the expanded, like one more way to write the Hamiltonian equation, still not full version. We can expand this into to get h h. We are not trying to expand the Hamiltonian, because we will fill it out in the end, because there's something we have to look at. So now this can further be simplified into h bar over 2m, and this. Okay, one more thing I forgot. This guy over here is square of the gradient operator, right? Now the square of a gradient operator is, now it's a this is a different operator. It's the same operator, it has a special name, which is known as Lap Laplacian operator, if I'm right. No, Lap 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 Laplacian operator. What was it again? I'm very bad with names. Laplacian operator. Okay. Now, when we talk about Laplacian operator, sorry for the mispronunciation. Now, this is a special operator which is square of the gradient operator, which is d over dx, which is nothing but d over dx square. Which is that's a square, right? So we don't have to look at it. Now it is a square and dx square. Now again we further expanded. Now we can further expand it as well. I could have done the expanding in one go, but that would not give us a very good visualization of the equation. So we can now h, which is also known as En, because h is actually an energy operator. Hamiltonian is an energy operator. Okay, the proper thing for Hamiltonian is an energy operator. So it's actually gives the energy of the physical quantity in a different situation, because situation to situation the energy changes. So that's why it's a reason that physical quantity in a different scenarios or different situations. So while now we'll expand this even further. I h bar d over dt is equals to minus minus h bar square over 2m d square over dx square plus. Now here we will be at, what I was not looking at is the potential energy. Let's suppose that the particle which we have, it has some potential again by like there is some force, some kind of force which is exerted on it, so which will be added as a potential. Okay, so that potential will be v in terms of x. Now still we don't have the proper form, we can even go further. Now it becomes I h bar d over dt equals negative of h bar square over 2m d square over dx square plus vx. Now what we are missing is something known as wave function. Okay, wave function, which is we know that wave function is a probability. Okay, if I want to express this, it's a probability. Okay, which it shows multiple probabilities of something happening, or a particle in being multiple states. That's called wave function. That's the actual meaning of wave function actually. And this is this. Even here we have to add, sorry. Now this is full version of Schrödinger equation. Now remember one thing, this t over here shows that it's a time dependent Schrödinger equation. Schrödinger equation. Okay, equation. And if we don't include this t, let's suppose we don't include t, it becomes a um, time independent Schrödinger equation. Okay, now there's one more expanding we can do. For that, wave function is e of e power I um, bracket kx minus wt. This is the wave physics function, wave physics. Okay, which is this is called a wave function. Mostly people ignore this wave function. So this equation can be written as, let me give me space. Now let me finish it off. I h bar d over dt lambda, sorry, wave function, so in vanilla wave function, e of I kw, sorry, not kw, kx minus wt is equals to minus h bar square e I k of w k of x minus wt over 2m, again d square e I kx minus wt. For the expanding, it's not finished yet. We have to complete this fully. This can be full, and it becomes plus x e. Don't have space, so I'll write it on the top. X minus k, sorry, wt. That's the full derivation. And one last thing, one last thing that it's finishing. That why I is not included here. Why is it not included? The reason for I not included is, it is, if we take square of I, square, what do we get? It cancels out, right? We get minus 1. So I for minus 1 is nothing. So yeah, that's it. Thank you.